Today we're going to look at some Laplace transform problems that are somewhat more complicated than last time, and they're going to involve something called the shift, and we're also going to be looking at more complicated partial fractions. So first, let's talk about the shift. The idea here is, suppose that we have e to the at times a function we know how to Laplace transform. Well, if we look at the integral definition, that's e to the at, f of t, e to the minus st dt. And now we can do a standard trick with the exponents we did before and rewrite this as e to the minus s minus at times f of t. Now, if we think of this s minus a just as s hat, a different variable, then what we've got is an integral from 0 to infinity of f of t e to the minus s minus at, and that's just this with the hat in it. And now if you look at this, that is the Laplace transform except in the variable s hat and not s. So this is f hat of s, okay, and that's the same cap f that we saw previously. And since cap s is s minus a, what we're really getting is the Laplace transform evaluated not at s, but at s minus a. And that's how e to the at times a function transforms. So as an example, Laplace transform of t squared we know is 2 over s cubed. So if we're transforming t squared e to the 3t, that's your e to the at, we're going to be getting the same thing, but not with s, but with s minus 3. So the Laplace transform is 2 over s minus 3 cubed. Now, important formulas in that regard are e to the at cosine bt and e to the at sine bt, okay? And those are just shifts of the old formula. Now, this one you may remember is s over s squared plus b squared. Same story, except s gets replaced by s minus a. And same deal here. The sine of bt was b over s squared plus b squared when it transformed, and now it's the same thing. It's just s is replaced by s minus a. Now, where does this come up? Let's take a look at the differential equation. X double dot plus 2x dot plus 5x equals 0. With the initial conditions, x of 0 is 2 and x dot of 0 is 0. Now, as we've seen before, you just transform the left-hand side, and by linearity, that's L of x double dot plus 2L of x dot plus 5L of x. And we've already seen how the second derivative transforms. Minus x dot at 0 minus sx at 0 plus s squared cap x. Now, this first derivative transforms as minus x naught plus s cap x times the 2 here, and then this transforms as x, and then 0 transforms as 0. We keep the s stuff on the left-hand side along with the cap x, and all the stuff from the initial conditions goes on the right-hand side. If we evaluate this properly, that's 0, that's 2, that's 2, 2 times 2 is 4, so we got 2s plus 4 on the top, and then we're dividing through by this. Now, this doesn't look like anything in our table, but we can make it look like something in our table by completing the square for the bottom. Okay, and now how do I know to complete the square and not to factor it? Well, b squared minus 4ac is negative. This thing does not have real roots. Okay, if it doesn't have real roots, what we're going to have to do is complete the square. We know that s plus a squared is s squared plus 2as plus a squared, and we want to complete the square down here. The correspondence is that this 2 is 2a, and that means that we want 2a to equal 2. a to equal 1, a squared equals 1. And that means that s squared plus 2s plus 1 is a perfect square. And we have 4 left over. So we can write s squared plus 2s plus 5 as s plus 1 squared plus 4. And we end up with cap x is 2s plus 4 over s plus 1 squared plus 4. Now, this denominator is looking a lot like a shift for sine or cosine, and indeed, the Laplace transform of e to the at cosine bt is s minus a over s minus a squared plus b squared. So what we need to do is s minus a is clearly here s plus 1. We need this top to be a multiple of s plus 1, which is why we take 2s plus 2. We take 2 of those, and there are 2 left over. Now that allows us to factor a 2 out, and we do have something that looks just like the Laplace transform of e to the at cosine bt. And what's left over is this term, which looks remarkably like the Laplace transform of e to the at sine bt. In fact, it matches exactly here. B is 2, and this is exactly that. So when we back transform, this thing becomes 2 e to the at cosine bt, and here a is minus 1, so it's 2e to the minus t. B is 2 cosine 2t. And then the sine term gives us an e to the minus t sine 2t. Now let's look at some problems that require a more extensive use of partial fractions than we've seen previously. So first example is x double dot plus 4x equals e to the 2t. X of 0 is 0, x dot of 0 is 2. So we Laplace transform the left-hand side, and we Laplace transform the right-hand side. X double dot translates as minus x dot is 0 minus x of 0 plus s squared cap x plus 4 cap x. But this time the right-hand side is not translating as 0, it's translating as the transform of e to the 2t, which is 1 over s minus 2. And when we move everything except the cap x's onto the right-hand side, we get that this moves over as a 2. This term is now 0. And there's the s squared plus 4 we picked up here. And when we divide through by s squared plus 4, we get 2 terms. 2 over s squared plus 4, which is really going to be pretty easy to deal with. And then this term, which looks like we're going to have to do partial fractions. Okay, so that is pretty clearly going to go back to a sine term. What about this? Well, s squared plus 4 cannot be factored any farther. It's an irreducible quadratic. There are no real roots. So in the partial fraction decomposition, we're going to have that in the denominator, and what sits over the top of that is as plus b. So you're looking for a general term that has degree 1 less than your denominator. So here it's as plus b. When we do this, we've got as plus b over s squared plus 4 plus c over s minus 2, standard decomposition. Multiply through. 1 equals as plus b times s minus 2 plus c times s squared plus 4. There are lots of ways to solve for a, b, and c. So one of the things you could do is you can just multiply this thing out. And what you end up with here when you do this is you got as squared plus bs minus 2as minus 2b. And here we've got cs squared plus 4c. We collect all the terms. The s squared stuff gives us an a and a c. The s stuff gives us a b minus a 2a. And the constant stuff is a 4c minus a 2b. And now that's got to match this thing, which is 0s squared plus 0s plus 1. Okay, so a plus c must be 0. b minus 2a must be 0. And 4c minus 2b must be 1. And now you can solve this system. That's actually not my preferred method. Okay, my preferred method is actually to look at this thing and say, hey, there are some good values I can choose for s. And one of the values that I can choose for s is 2. And if we do that, this term vanishes, and we get c times 4 plus 4, which is 8, and c is an eighth. Now, it's not so obvious what to do with this term until you think about, well, you know, the roots are plus or minus 2i. What if I substitute 2i? And that's what we're going to do. And when we do that, this term is gone, and this thing becomes 2ai plus b times 2i minus 2, and we just multiply it out. And the real stuff, we're going to get a minus 4a from here. We're going to get a minus 2b from there. And then the imaginary stuff, 2b minus 4a. And that means 1 is minus 4a minus 2b plus 2b minus 4ai. And this is 1 plus 0i. So that's got to be 0. And this is 1. So we now have that system. 1 equals minus 4a minus 2b, and 0 equals 2b minus 4a. And this one is really easy to solve. B equals 2a. You plug that back into here. Minus 4a equals 1. A is minus an eighth. And when you plug into b equals 2a, you got b is minus a quarter. So when we substitute a, b, and c back into the partial fraction decomposition, we get 1 over s minus 2 times s squared plus 4 is as, which was minus an eighth, plus b, which was minus a quarter, plus c, which was an eighth, and that gives us our decomposition. And we're now going to break that up as minus 1/8 times s over s squared plus 4. And now this is minus a quarter, but we're going to want to transform back to sign. So we want s squared plus 4 in the denominator and 2 in the numerator. So we write a fourth as minus an eighth times 2. And then we got 1/8 times s minus 2. Now remember that our original Laplace transform had two terms. The one that we did the partial fraction decomposition on, and a 2 over s squared plus 4. Okay, so back transforming, this term goes back to minus 1/8 cosine 2t. This term goes back to minus 1/8 sine 2t. This term goes back to 1/8 e to the 2t, and then this term goes back to the sine of 2t. You add everybody up, and you get minus 1/8 cosine 2t plus 7/8 sine 2t plus 1/8 e to the 2t. Last example, we want to look at x double dot minus 3x dot plus 2x equals e to the t. X of 0 is 6, x dot of 0 is 0. So we do our standard thing, x double dot transforms as minus x dot of 0 plus sx of 0 plus s squared cap x. X dot transforms as minus x is 0 plus s cap x. That's multiplied by the minus 3 plus 2 cap x from here. Transform of e to the t is 1 over s minus 1. And now when we collect all the terms, the cap x stuff, we got an s squared, we got a 3s, we got a 2. We've got this 1 over s minus 1 from the right-hand side, and then the initial conditions go over as s times x naught, which is 6, and then minus 3 times minus x naught pops over here. We get a minus 18. And we finally divide through, and we get cap x is 1 over s minus 1 divided by s squared minus 3s plus 2 plus the initial conditions 6x minus 18 divided through by s squared minus 3s plus 2. We note that s squared minus 3s plus 2 factors as s minus 1 times s minus 2. And if we do these terms individually, we're going to end up doing two partial fractions. So what we're going to do is we're going to put them over a common denominator, and that's the common denominator. So this thing gets multiplied by s minus 1 over s minus 1, and we pick up a 6s minus 18 times s minus 1 from this term, a 1 from this term, all over s minus 1, which is this s minus 1, this factorization here. And now when you multiply out the top, you get 6s squared minus 24s plus 18 plus 1 is 19 over s minus 1 squared times s minus 2. Now what we've got here that we haven't seen before is a term that's squared. And what you remember, I hope, is that when you have a term like this, you do what you would do normally in terms of the partial fraction decomposition if it were to the first power, and then you do the same thing, but now it's to the second power. And if it were a cube, you'd do it again to the third power, but here we've only got a square, and then of course this is the standard thing you do with an s minus 2. Okay, we're going to multiply through, and we get 6s squared minus 24s plus 19 is a, and now we get a cancellation with one of the s minus 1, so we get an s minus 1 times an s minus 2 here. Both of the s minus 1s cancel here. We got a b times s minus 2, and here the s minus 2 cancels, and we get a c times s minus 1 squared. Now, what we're going to do is look for good things to substitute in for s. S equals 1 is an obvious choice. So we lose this term, we lose this term. B times 1 minus 2 is minus 1, so this is a minus b. Here we're plugging in 1, and that gives us 6 minus 24 plus 19. And when you add that all up, you get 1, which is minus b, so b is minus 1. Now, another obvious thing to put in is s equals 2. And what's going to happen is this is going to vanish, this is going to vanish, and this thing is going to become 2 minus 1, which is 1 squared, so we're just going to get a c. And now when you put 2 in for s squared, this is a 24, this is a 48, this is a 19. When you add these things up, you get minus 5, so c is minus 5. Now, we're sort of out of good things to plug in terms of killing off terms. However, we know b and c, a is the only thing that remains to be determined, so let's put in a value of s that makes this relatively painless, and s equals 0 looks like as good a choice of any. So when we put it in on the right-hand side, we're going to get 19. Here, minus 1 times minus 2 times a, 2a. Here, b times minus 2, or minus 2b. And here, c times minus 1 squared, or c. So we've got 19 is 2a minus 2b plus c. And we know that b is minus 1, so when you put that in here, you get a plus 2. And we know that c is minus 5, so when you put that in here, you've got 2a plus 2 minus 5 equals 19, which means 22 is 2a, and a is 11. So a is the thing that goes over s minus 1, b is the thing that goes over s minus 1 squared, and c is the thing that goes over s minus 2. Now this piece we recognize is going to 5e to the 2t. This piece goes to 11e to the t. This one is a shift. 1 over s squared goes to t, and we're just shifting that. So we're going to go to t e to the at, and a is 1, so we've got a te to the t, and our final answer is 11e to the t minus te to the t minus 5e to the 2t.